Should we go back and reenact the situation?
Reenact.
So,
scroll up and say, this is what we're doing.
yeah, we need to. Here's what we're doing. All right, there we go.
Pause the video right there.
Yeah. Yeah.
Now, if you're wondering what we just did,
We asked the same question.
So, domain is found along the x-axis. Another word for domain is inputs or x values. Yeah. Wait until we're done. You can wait. So looking along the x-axis, we got to determine which x values are in the domain, which ones are not. And it was kind of like number 49 or 53, the problem that we were talking about earlier. Do you see where my pencil's pointing right here?
Yeah.
This corresponds to x equals 3. Is 3 in the domain of this function? It is not. If we come up from 3 or down from 3, there aren't any corresponding function values there. 3 is not in the domain. Okay. What about positive 1?
Yeah.
Yes, it is. Because here's where x equals 1, so that's in the domain. 2 is in the domain. What's the highest number in the domain?
2.
2 is the highest number. Okay, if we go the other direction, negative 3 is the smallest number, including both endpoints, so it's going to be negative 3 to 2. Domain is found along which axis? The x-axis, because domain is the set of all possible inputs. Inputs are the x-axis. Yeah. Yes. Yep. Ooh. Then it technically wouldn't be a function. That would be an inequality, but that's a good question. The range is along the y-axis, but it's found the exact same way pretty much. You're just looking along the y-axis now. Here's where the y values correspond to negative 2. So is negative 2 in the range? Negative 2, is it in the range?
No.
If I come across from negative 2, I do not hit the graph anywhere. There's no points on the graph corresponding to a y value of negative 2. What about negative 1? Is negative 1 in the range? 0. 0 is in the range. And every number between 0 and what? Every number between 0. Every number between 0 and 3. Okay, including both of those. Let's try another one. Yeah. In an interval, the smallest number always has to come first. The largest number has to come last. That's a good question. Let's try example 2. Draw this graph.
Is that an open circle?
That is an open circle, yeah.
Question: how often would we see a graph like that in day-to-day life?
At this point in your life, probably not very often.
I mean, you know.
I was thinking the same thing about piecewise functions.
Okay, those kinds of questions, I know that they exist in your mind, but there really isn't a point discussing why do we need to learn this, when do we ever use it. I mean, the point is we have to learn it. It's part of the 1050 curriculum. So, just a pill that we got to swallow. Not everything that we are going to learn in this class is applicable to daily life. It's just stuff we have to learn.
If you do physics, then it will all make sense.
For the most part. So, domain. Domain, you guys.
You got it.
Is negative 1 in the domain?
Yes.
No.
No. What was I saying?
The graph originates from x equals negative 1, but at negative 1 we have to place a parenthesis around it because the graph doesn't exist at x equals negative 1. Now, if we continue to the right on the x-axis, all of these numbers are in the domain because they have corresponding function values. How far on the x-axis could I still find function value? Yeah, all the way out to positive infinity. So the domain is from -1 to infinity, but not including -1. Okay. Range is similar. It's not exactly the same. If we take a look along the y-axis, what value on the y-axis? What's the lowest value on the y-axis where we can find function values corresponding to that y value? -1 is down here on the y-axis. So it's 0. The lowest number on the y-axis is 0. So it's 0 to infinity. Okay? That's really all you can expect from that first objective, finding domain and range, by looking on a graph. Are there any questions on domain and range? Let's move on. This is probably a new topic. Intervals. Of increase and decrease. Let's take a look at a graph that hopefully you are all familiar with. Example 3. This is objective 2 now. So draw the parabola. I'm going to put some points on the left side of this parabola all the way down to the very bottom. Now, I don't know the exact value of these points, and that's not important, but the point is each of these points have an x number and a y number, correct?
Yeah.
Now, regardless of their exact value, I want you to consider the x values. Are you guys ready? Consider all of the x values of these points. As I move from left to right, what x value are they all approaching?
0.
What x value are they all approaching? They're all approaching 2, right? Because what happens at 2? Well, the points kind of switch from going downward to upward. So all of the x values are approaching 2. Can we see that? Now, what's happening to the y values? Are they increasing as I move from left to right, or are they decreasing?
Decreasing.
The y values are decreasing. Up until which x value? When x equals 2, what do the y values start to do again? Increase. This is how we describe intervals of increase and decreasing. But the most important thing students need to remember, intervals in increase and decrease only involve x values. When you describe an interval on which a function is either increasing or decreasing, you only use the x values along the x-axis. Okay? So if I were to extend this graph all the way out as far as I could to infinity and to negative infinity, let me actually do this a little bit longer. So if I took this graph and extended it way out to here and way out to here, all of these points I've labeled in red. The y values of each of these points, what's happening to the y values as I move from left to right?
They're going up.
The y values are decreasing. Okay, so I'm going to say this function is decreasing on the interval Now I have to choose an interval of only x values. For which x values is the function decreasing, or are the function values decreasing?
Anything to the left of 2.
Anything to the left of 2, correct? If an x value is to the left of 2, doesn't that correspond to a decreasing interval of the function?
Yes.
How far to the left of 2 does the function decrease?
Negative infinity.
From negative infinity. And it continues to decrease. So if I started all the way at negative infinity, the function is decreasing all the way up until which x value? 2.
Would you put a parenthesis?
You do put a parenthesis. Now I have to clarify something here. Our textbook, for some reason, is wrong. I don't know why they haven't fixed this yet. But if you were to check your answer in the back of the book on a problem like this, they would mistakenly put a bracket there. It is incorrect. Okay? Intervals of increase are what are called open intervals. So you leave it open. You don't close it with a bracket. Okay? It's decreasing on the interval, negative infinity to positive 2. Yeah?
So if it's, even if it's like, this graph that has closer intervals,
Correct, yeah.
always negative.
It's always an open interval for increasing or decreasing. Now, these points I'm labeling in blue. What's happening to the y values of each of these points? So that's an interval of increase on a graph. We have to describe the x values on which that occurs. So it's increasing on the interval. It's increasing on the interval. So where does it start to increase? Where x equals 2, not including 2, but just an open interval of 2. And it continues to increase to infinity. So these are the intervals of decrease and increase on this particular function. If I had flipped this parabola upside down, and I kept the vertex in the same spot, I just flipped it upside down, then from negative infinity to 2, it would be increasing, and then from 2 to infinity, it would be decreasing. Let's see if we can take a look at another one here. Let's do example 4. So more likely than not, you're going to have a function with multiple increase or multiple intervals of either increasing or decreasing. So let's start with let's try to find, there may be more than one interval in which the function is decreasing, so we have to find all of them. First thing you ought to identify is where does the function switch from either an increasing or a decreasing. Okay? And that's actually, we're getting a little bit ahead of ourselves here, but this is objective 3, but those are called the extrema of a function. Where a function switches from an increasing to a decreasing or from a decreasing to an increasing, that's called either a minimum or a maximum, a local minimum or a local maximum. For example, this point right here, do you see where my pencil's pointing? In that general area, so I'm going to just circle a small, this is called a neighborhood of a function. In this small neighborhood that I've chosen, is there any other higher point than that point right there? That's what's called a local maximum. It may not be the overall highest point of the entire function, but in this neighborhood of the function, isn't that the highest point? That's what's called an extremum, or a local maximum in this case. And what happens to the function at this point? Well, it switches from an increasing to what? A decreasing. So we have an extrema right here. Now it's decreasing down to this point. Is this the absolute lowest point on the entire graph? No, but in a small neighborhood of the function, isn't that the lowest point in that neighborhood? So that's called a local minimum. And what happens at that minimum? It switches from a decreasing function to an increasing, or a decreasing interval to an increasing interval. And that's really all objective 3 is identifying either local minimums or local maximums on a graph. It's a pretty easy objective, but we'll get to that in a second. So how do we describe intervals where it's decreasing? This one right here, isn't this an interval of decrease? So between which two x values is that occurring? -2 and -1. So it's decreasing on the interval -2 to -1. Okay. And now, once it passes by this local minimum, it starts to increase again. So we have an increasing interval right here. But And then the function, once it reaches that local maximum, begins to decrease again. So now we have another decreasing interval right here. So on which x values is that occurring? Positive 1 to infinity. And we put a union symbol between that. Those are the intervals of decrease. Now we locate some intervals of increase. I've already got one here in blue, but this other one right here, the function is increasing on that interval because the y values are increasing as you read the graph from left to right. Only x values. We only use x values. So between which two x values is this increasing? -3 to -2 union. -1 to +1. Okay, that's really all there is to increasing and decreasing. You only use x values. You only use parentheses, no brackets. Okay? And just to tie this into objective 3, what's the significance of when a graph switches from increasing to decreasing or decreasing to increasing? What happens there? What do we find? We find extrema, either a minimum or a maximum of the graph. They're not the overall highest or lowest point. They're called local minimums or local maximums. Okay. So for example 5, let's use the same graph. Example 5. I'm going to say find all local extrema of the graph from example 4. So using the same graph, we need to locate the points at which the function is switching from an increasing to decreasing or decreasing to increasing. And there's a specific way I want you to answer this. So pay attention to how I would like this answered. So let's talk about this point right here, the one that I've put a star by in blue. In that general area of the graph, that's the highest point, right? So we call that local max. Now the maximum value is the y value at which that occurs. So considering that point, what's the y value of that point? 3. So we would say the local max is 3, but now we have to state the x value at which it occurs. So the local max is 3 when x equals -2.
What about 1?
Now, you do notice right across the y-axis, isn't there another local max of 3 right here? But it has a different x value. So the local max is 3 when x equals -2 and when x equals +1. So we have two local maximums. Okay, and if we consider this point down here, this is another point at which the function switches from an increasing, or in this case, yeah, it's decreasing, then it switches to increasing, so that's an extremum. But we would call that a local minimum. And again, it's the y value that we described. What is the y value of that point? 1. So the local minimum is 1 when x equals when x equals -1. Just some follow-up questions from the last assignment, or the last assignment. Hold on one second. Would that be the graph of a function?
Yes.
How come? it passes the vertical line test, so it is the graph of a function. I'm going to ask a follow-up question here. Part of example 5. What's the domain?
Negative.
The domain, what do you guys think? We said -3 to infinity, including -3?
Yeah.
Okay. And the range, remember, in an interval, the left number is the smallest number. This graph does go down to negative infinity on the y-axis. That's the smallest number. Negative infinity is the smallest. So when we're describing an interval, that's got to be the number on the left. So negative infinity. And then up to what point does the range reach? +3, including 3. Okay. So in terms of finding relative what does the book call it? Local minimums, local maximums, or local extrema. You just got to look at the graph and find places on the graph where it's switching from an increasing to decreasing or vice versa. Okay? Yeah.
So why is the first point, -3, 0, not considered an extrema? Because it's a local minimum.
We could. It's technically not a part of the graph where it's switching from increase to decreasing, but you could actually state that as a local minimum. Yeah. Yeah.
How would you find like the intervals of increase and decrease on, I guess, for a function?
Like a cosine graph?
Yeah.
They would have an infinite number of increasing and decreasing so the question was, and that's not something you'd have to do in this section of the book, maybe later on when we get into trigonometry, but that's not till March. So, do you guys remember what a cosine graph looks like, or a sine graph? Sine graph starts at 0, 0, and just oscillates between 1 and -1, so it goes up and down and up and down. So yeah, it would have an infinite number of increasing and and the other tricky thing is how the graph is labeled on the x-axis. Do you remember this from Algebra 2 last year? The x-axis is labeled as pi fourths, and then we had pi halves, and then 3 pi over 2, and just some weird values, so that it could still work. It would. It's not something we're expected to do at this point. Maybe later on. But just looking at this, what would we consider this point to be? Local maximum of 1 when x equals pi fourths. So, and there are an infinite number of minimums and maximums on this graph as well. Good question. So let's see, did we do everything we needed to do? We found the domain range, we found intervals, function, increase, decrease, we found local extrema. The homework is going to throw out some interesting questions. Let's do one more example. This is example 6. Your homework is also going to ask you to interpret a graph other than just finding its domain and range. And they're pretty interesting questions.
Figuring out the functions for it?
Not exactly. That would be an interesting question, though. Okay, so 1, 2, 3, 4, 5, 6. So try your best to put those points in the exact same spot I have them. This is 4 over here. This is 7. This is 4 on the y-axis. That's 7 on the y-axis. Yeah. So you have a homework question very similar to this one, where it gives you some funky looking graph like this that's on the XY plane, and it gives you specific labeled points that you can look at. And it's going to ask you a bunch of questions related to this. So for example, they're going to ask you to find f of negative 2 and f of 4 and f of 7. Now normally when it asks you to evaluate a function, what have we done in the past? We've taken that number in the parenthesis and plugged it into the equation of the function. Well, we don't have the equation, and we don't need to find the equation of this graph. We can do the same stuff graphically. Is this an x or a y number that I'm pointing at right here? It's an x number. And once you plug it into the function, it spits out the y value. For example, if we did have the equation, let's say that the equation was 2x squared minus 3, we would plug the negative 2 in for x, and the resulting number would be the y value, correct? So what they're asking us to do is find the y value of this function f when x equals negative 2. So you go on the x-axis at negative 2. What's the corresponding y value? 4. So what is f of negative 2? What's the value of the function f when x equals negative 2? 4. Okay, because this point right here corresponds to the point negative 2, comma 4. So right there that tells you when x equals negative 2, what does y have to equal? 4. So instead of having to plug this into an equation and evaluating it, we just look, okay, here's where x equals negative 2. Y equals 4 there. What about f of 4? When x equals 4, what is the function value? Well, here's where x equals 4. The point there is 4 comma 4. So f of 4 is equal to 4. Okay. F of 7, if we go over to 7 here, this is the point 7. Let's see, that's 7 comma 7. So when x equals 7, the function value is 7. Okay. Here's an interesting question. Find all values of x for which f of x equals 4. Find all values of x for which f of x is equal to 4. Now, it's not nearly as complicated as it sounds. F of x really just stands for y, correct? So all they're asking you to do is find all points on the graph that have y values of 4. And then what are those corresponding x values? So looking at the graph, what are all the points on the graph that have y values of 4? Here's one right here that has a y value of 4, and here's one right here that has a y value of 4, and all the question is asking for are the x values of those corresponding points. So which x values have f of x equal to 4? X equals negative 2, and x equals positive 4. All right. Find all values of x for which f of x is greater than 4. Yeah. Intervals, yep, these are intervals. Find all values of x. There are tons and tons and tons of values of x for which f of x is greater than 4. So rather than listing them separately, we are going to do it in an interval. So consider this. This point right here, the one in blue, does this correspond to an f of x value greater than 4? So this point is not included because it's not greater than 4. But what if I just go barely above that? Isn't this point, doesn't that have a y value greater than 4? This has a y value greater than 4. All of these, so I'm going to do the one in red. The one in red, that does not have a y value greater than 4. Is there other points on the graph that do not have y values greater than 4? This one over here, this point, does that have a y value greater than 4? No, it equals 4, but is it greater than 4? But any other point you choose on the graph, all these ones in blue, don't all of these points correspond to y values that are greater than 4? So we need to list all of those x values. Now, is it just the x values of these blue points I've listed, or are there points between these blue points?
It's an infinite.
There are an infinite number of points between any two points you can choose on a graph. Okay, so how do we list an infinite number of x values in an interval? So, for example, between these two red dots, what are x values between these two red dots?
-2 and 4
With parentheses, yeah. Between -2 and 4. If x is something between -2 and +4, not including -2 and 4, you're going to have a y value or an f of x value that's greater than 4.
And we do union.
Union.
4 and +4 and then +7.
And then in this interval right here, all of these points in this interval correspond to y values greater than 4. So this is from 4 to 7.
7's in the bracket, isn't it?
Yeah, well, actually it is. That's really all you can expect from 2.3. Let's just double check, you guys. Ask yourselves internally, okay? Do you know how to find domain and range on the graph of a function? Okay? Do you know how to find intervals where the function is increasing and decreasing? Okay? And can you locate local extrema? Okay? All right.